The analysis performed here is looking at FPV racing drones and their aerodynamic efficiencies. The sport of racing FPV drones is very much in its infancy, and as such, the technologies incorporated in even the most successful racing drones are relatively lacking from an engineering standpoint. Currently, they have little to no consideration for the aerodynamics, and as can be seen here, this is a current configuration of modern design, and it's essentially a flying brick. The intent of this analysis is to compare modern configurations with streamlined configurations to demonstrate the increase in aerodynamic efficiency by choosing a geometry with a lower drag coefficient, thus reducing the drag force. Let's take a quick look at some of my research in the field. Now let's talk about the governing equations for this system. The analysis was performed at 50 miles an hour, 22.35 meters per second, which was determined to be the average speed of the drone while racing in competition. Due to the relatively low velocity, the flow was assumed to be incompressible. With that in mind, the solution is governed namely by the incompressible Navier-Stokes equations. To represent the turbulence of this model, the K-epsilon model was used, involving the turbulent kinetic energy and the kinetic energy dissipation equations. To find drag force, the aerodynamic drag force equation was used. For the discretization of the problem, the solution was found using the simple scheme with pressure-velocity coupling influence. Discretization was as follows. The gradient used the least squares cell-based method. The pressure was a second-order discretized. Momentum was second-order upwind discretized. Turbulent kinetic energy was first-order upwind discretized. And specific dissipation rate was first-order upwind discretized. For the geometry and meshing of the problem, to set up the geometry constraints for the problem, SolidWorks models were created for a drone with and without an aerodynamic shell. An enclosure was then set up in ANSYS of air. The drone shape was then subtracted from the air enclosure. The mesh was then generated using a curvature size function set to medium relevance center. The setup reached acceptable convergence and model representation, ensuring the solution is stable and accurate. For the problem closure, the boundary conditions for this problem were generated by creating an enclosure around the drone geometry. The boundaries were set up with an inlet and exit at the front and back of the drone respectively. For initial conditions, the solution was found with an initial velocity set of the air representing the drone moving through the air of the 50 miles per hour, and that came in at the inlet. The results of this analysis yielded pressure, drag force, and velocity profiles for the experiments. As can be seen in this picture here, the pressure on the brick drone is much higher and much more concentrated than that of the contoured shape. For the velocity profile, we can watch some videos of the streamline behavior. This shows that the streamlines are able to move much more easily around the curved shell than that of the brick shape. For the force graphs, this is very similar to the pressure contours in the fact that the brick-shaped drone represents a lot higher force concentrations, and the shell drone has a lot less force acting on the drone, which allows it to ultimately attain a higher velocity with the same thrust. As was demonstrated by both the pressure and force contours, the shell configuration increases the aerodynamic efficiency of the drone. The decrease in that drag coefficient and subsequently the drag force on the drone will allow the drone to travel at a greater velocity with the same amount of thrust from the propellers. With that being said, the largest factor in being competitive in FPV racing is still, by a large margin, the skill of pilot. Let's take a look at a few more clips of my research.